Assalamu alaikum students. So today we are going to start chapter 11, which is about the phase transitions. So concept of phase transition is very important in chemistry, thermodynamics and other related fields. What are the phase transitions? Phase transitions are the physical processes um, of transition between the basic states of matter such as solid, liquid and gas, as well as plasma in some rare cases. So when a system is cooled, new states of matter can appear. For example, a gas when cooled forms a liquid, whereas the liquid when cooled forms a solid, or it can become a superfluid as well. A superfluid is a fluid which can flow without resistance. So we describe a state of matter as gas, liquid, and solid, and the transition between these states is known as a phase transition. So, what is meant by the term phase? A phase is a state of matter which is uniform throughout, not only in chemical composition but also in the physical state. That is, the uniformity is crucial. That is, the properties such as the density and conductivity of the system must be the same, as well as the chemical composition throughout the system. So let's try to understand the nature of phase transition, and by applying a heat to a piece of ice, and let's see what happens to the temperature of the ice. So let's draw a curve. Let's apply heat at constant rate to a piece of ice and draw a curve between the temperature and the time. And here the scale will be in Celsius, and we know that the 0 degree Celsius is the temperature at which the ice converts into a liquid, whereas the 100 degrees Celsius is the temperature where the liquid converts into a gas. That is, it's the boiling point of a liquid. So initially, the block of ice will be at certain temperature below 0 degree Celsius. So when the temperature is when the heat is supplied, the temperature of the ice will increase up to a certain temperature, that which is the 0 degree Celsius, because this is the temperature at which the ice will start to melt. And you will see that after reaching 0 degree Celsius, there will be no increase in temperature of the ice until all this solid ice has been converted into a liquid. Similarly, once all the solid has been converted into a liquid, then you will see that the temperature of the liquid will start to rise again, and then it will rise up to a certain temperature, which is the 100 degrees Celsius. That is the boiling point of water. And once the boiling point 100 degrees Celsius is attained, again the temperature of the system stops to increase, and again it will stop to increase for a certain period of time until all the liquid has been converted into a gas. And so once it's converted into a gas, again we will see an increase in the temperature of the system. So what we can note from this curve, from this graph, is uh, that the gradient is different in both these cases. That is, this gradient has more steeper slope than this one. So this can be explained on the basis of the difference in heat capacities uh, ice and water. That is, ice has lower heat capacity than water. And also, one more point that we can note here is that that it takes energy to convert the solid into a liquid, and again, it takes energy to convert a liquid into a gas. That it takes more energy to convert a liquid into gas as compared to that of energy required to convert a solid into a gas. And this energy can be quantified, and it is quantified in terms of the latent heat of the system. So, a latent heat latent heat is defined as the energy needed to uh, convert one state of matter into another state. So, in case of the ice, it is known as the latent heat of fusion. So it is the energy required to convert a solid into a liquid per unit mass. Whereas in case of the liquid, it is known as the latent heat of vaporization, which is the energy required to convert the liquid into gas per unit mass. And also there is another latent heat of sublimation, and if and it is associated with the transition when the system goes from directly from solid to the gaseous phase. So what we can see here is that 2.22 kilojoule per kilogram per Kelvin is the value of the specific heat of ice, and whereas the latent heat of fuel for ice is 333 kilojoule per kilogram. So what is meant by 2.2 kilojoule per kilogram per Kelvin is that 2.2 kilojoule energy is required to increase the temperature of 1 kilogram of ice by 1 Kelvin. And if we compare this number of specific heat with the specific heat of liquid water, we can see that the specific heat of liquid water is 418 kilojoule per kilogram per Kelvin. It means that much more energy is required to increase the temperature of 1 kilogram of water to by 1 Kelvin. So that's the reason that why it takes more energy to convert a liquid into gas. So let's move forward and uh, try to understand the nature of this phase transition. So, in order to understand the nature of these phase transitions, we have to devise some mechanism by which we can explain all types of phase transitions. So, here we shall explore the nature of phase transitions by using simply the idea is that the most stable state of matter is the one with the lowest thermodynamic potential. We know that whenever a system is stable, we say that the system will be in its lowest energy state. That is, the system minimizes its energy, minimizes the energy of the system to attain that low stable state. So, in general, we can say that whenever we have a stable phase, there is some thermodynamic potential which is minimized. So, whenever a phase has a stable phase has the lowest thermodynamic potential, that phase will be the stable, will be the most stable phase. So, whichever phase has a low thermodynamic potential is stable. The phases which have a higher thermodynamic potential are unstable, and they decay into a stable phase. So, what we are going to do here is we know that there are different kinds of thermodynamic potentials involved in different systems depending upon the constraints which are imposed to the system. We know that there is a Gibbs free energy, which is one type of thermodynamic potential. The other is the Helmholtz free energy. We know that there is also a grand potential, and for the case of magnetic system, there is the magnetic free energy. So all these different types of energies are the thermodynamic potentials, and all these energies are being minimized to attain some stable state of the system. So how we can define this thermodynamic potential? So which the thermodynamic potential is defined as the function which is minimized subject to all the constraints that are imposed on a system. Okay. So, what is meant by constraints? Because we know that for the case of a Gibbs free energy, that when the thermodynamic potential is the Gibbs free energy is the relevant energy for the system, which are held at uh, a constant pressure and has a fixed number of particles. And this is the system in which the volume and energy basically they varies to minimize this Gibbs free energy of the system. If we recall from chapter 5, we know that Gibbs free energy is related to a system where the system of interest is connected to some reservoir which has some fixed temperature and fixed pressure. So the temperature and pressure of this system is defined in terms of the temperature and pressure of this reservoir at the equilibrium. And basically this system varies its volume, and it minimizes the Gibbs free energy of the system. Similarly, in case of, if we talk about the grand potential, in case of the grand potential, the quantity which varies is the number of particles. So again, in case of the grand potential, we know that a system of interest is connected to a reservoir which is at temperature T, and has a chemical potential mu. So again, these this temperature and chemical potential will be the temperature and chemical potential of the system when the equilibrium is reached. So it means that in grand potential, the system varies the number of particles in order to minimize this energy, which is the grand potential. Whereas in case of the Gibbs free energy, the system move towards the most probable state, or moves towards the minimum energy state by varying the volume of the system. And similarly, in case of the magnetic free energy, the parameter which varies is the magnetization. So the system varies the magnetization in order to minimize the magnetic free energy of the system. Similarly, another energy of interest is the Helmholtz free energy, which is defined for a system which are held at constant volume and temperature. So all these different types of thermodynamic potentials, all these are the different types of thermodynamic potentials, which are minimized depending upon the constraints which are applied to these systems. So here, what we are going to do is that we are going to define a general mechanism for all kinds of phase transitions, for all kinds of thermodynamic potential. So what we can do here is that we can denote this Gibbs free energy, or Helmholtz free energy, or magnetic free energy, or grand potential, which are being minimized by a similar symbol, which is this capital phi, and the term which, and the parameter which is in the bracket represents the parameter which basically varies to minimize this thermodynamic potential. Whereas, so in case of Gibbs free energy, volume of the system changes to minimize the this thermodynamic potential, which is the Gibbs free energy. So again, I have written here that phi of phi can be called as a generalized thermodynamic potential. So by generalized thermodynamic potential, I mean that the system is not at equilibrium position. That is, the system has to vary this parameter which is in this bracket, uh, and this parameter will be varied to minimize the free energy, to minimize the thermodynamic potential. So I will call this capital phi as the generalized. So the energies will be called the generalized Gibbs free energy, generalized Helmholtz free energy, and generalized magnetic free energy, and generalized grand potential. If we recall from quantum mechanics, we know that the thermodynamic potential can be thought of as analogous to the potential energy Vx of a particle in a one-dimensional box. And we know that when we see that when we say that the particle is in its lower energy state, we can picture this lower energy state as the particle sitting in some potential at the bottom of the potential band. So similarly, this picture can also be uh, taken in this case, and in this situation, the thermodynamic system basically lowers its energy by sitting at the bottom of this thermodynamic potential. So this phi will vary to bring the system to this equilibrium state. So this bottom of this potential well will represent the most stable state, which will be the equilibrium state of the system at which the entropy of the system is maximum and the system is in its most probable state, which is the most stable state of the system. So phi of I is basically a generalized thermodynamic potential, which can represents the Gibbs free energy or Helmholtz free energy and so on. So one potential well, the minimum of one potential well will represents the stable state of one particular phase. And similarly, in case of phase transitions, when the system goes from one stable state to another stable state, we can think of it in terms of two minimas. That is, one minima will represent the stable state of one phase, the other minima will represent the stable state of the other system. For example, this minima could correspond to the liquid phase, whereas this could correspond to the gas phase. So, uh, the system will be present in that energy state, will be present in that phase which has the lowest thermodynamic potential. So in this case, this minima has the lowest energy compared to that of this energy. So it means that in this case the most stable phase will be the gaseous phase. But we know that when we vary some parameter, for example, temperature in this case, so that when the temperature of this increases, um, the gaseous phase can convert into some other phase, or the liquid phase can convert into some other phase. For example, if we increase the temperature of this liquid after a certain temperature, you will see that this liquid phase will convert into a gaseous phase, and that's the temperature of, and that's because of the phase transition. So you can picture this as that when the temperature increases, this minima will vary. Both of the minima will vary, and they will vary with different rates. And at one point, you will have two minima which are equal, which have equal depth. So this is the in this stage, at this stage, the system is can be thought of as equally stable in both these minimas. So when you further increase the temperature, this first minima will have lower energy compared to that of this minima. In that case, in this case, the other phase will be more stable. So now the system will switch from this phase to this phase. So it means that the phase transition can be thought or can be represented as two minima, and as the temperature changes, the minima changes position relative to each other. So whichever minima has lowest energy, the system will be present in that energy state. So um, how we can picture this phase transition is that initially the system will be present in one stable state, and you are increasing or lowering the temperature of the system. Another minima will start to appear, and the minima, the depth of this minima will start to increase with increase in temperature. At a certain time, both minimas will be equal, and finally you will see that there will be a point when the system will become unstable and it will decay into some other state. So this is the point which is the point of phase transition, and after the phase transition the system will remain in this state which is the other, which can be other state of the system. So this is basically a model of uh, phase transition. That is, on increasing the temperature or decreasing the temperature, the minima will evolve, and the second minima will be established. And at some stage, particular temperature, the system will go from one minima to the other at the phase transition. So now let's discuss different types of phase transition. There are two types of phase transition. The first one is known as the first order phase transition, and second one is known as the second order phase transition. Second order phase transition will be discussed in next lecture, whereas now we will discuss about the first order phase transition. So first order phase transition uh, is the one which shows uh, a discontinuity in one or more of the first derivative of the thermodynamic potential. Suppose that the thermodynamic potential phi depends on some set of constraint parameters xi. If any of the first derivatives of this thermodynamic potential are discontinuous at the phase transition, then it is known as a first order phase transition. So what is important to note that if any one of the first derivatives of shows discontinuity, then it can be regarded as a first order phase transition. So for example, suppose that the thermodynamic potential is a Gibbs free energy G with constraint parameters T and P. So by slightly changing the constraints, we generate a small change in G, as dG is equals to minus SdT plus VdP. So this expression can be easily established because we know that G is given by H plus PV and H is equals to U plus PV. So if you differentiate and use the first law of thermodynamics, you will reach this expression that dG is equals to minus SdT plus VdP. So that we can write this as uh, S is equals to minus partial G by partial T at constant P, and V is equals to partial G by partial P at constant T. So at the phase transition, if G with respect to T is discontinuous, there is an abrupt change in the entropy of the system as the phase changes. And also, if G with respect to P is a discontinuous, there is an abrupt change in volume uh, at the phase transition. That is, if we go from one phase to the other, there will be an abrupt change in the volume of the system. And the common example is the liquid solid transition, which is an example of the first order phase transition. So, in order first order phase transition, any of the first derivative of the Gibbs free energy is discontinuous. So the entropy of the system can change when we go from one stable phase to another, or the volume of the system can change, or there are different properties, other properties which will vary as well. So how we can show these phase transition, and we can show. So here we are showing the discontinuity in the phase transition. That this is the phase, this is the transition temperature. So this is the first stable phase, and this is the final stable phase of the system when we are increasing the temperature. And at the phase transition, there is a discontinuity in the entropy, and similarly there is a discontinuity in the volume of the system as well at the phase transition. So an important point to note is that the Gibbs free energy is continuous at the phase transition for the first order phase transition, and this point we will discuss uh, later, that why the Gibbs free energy is continuous at the phase transition. And also some other examples of phase transitions are the heat capacities, which also shows a discontinuity in the first derivatives at the phase transition. So all these different examples are the examples of um, first order phase transition, that is a transition from liquid to solid, or liquid to gas. There are the first order phase transitions. So we can also show these first order phase transitions by phase diagram. But before going to the phase diagram, let us draw an expression for the latent heat which is involved in the first order phase transition. As we discussed at the start of this lecture in figure 1, that whenever you heat a piece of ice, the temperature of the ice will increase, and when it reaches 0 degrees Celsius, the temperature stops to increase for a certain period of time. And that is the period when the system absorbs the heat um, uh, from some external source. And that absorbed heat is basically the latent heat of fusion or latent heat of vaporization in case of liquid gaseous transition. So, whenever there is a phase transition, as we already discussed, there is an abrupt change in different properties of the system. That is, the entropy of the system will be different uh, in both phases. The volume of there will be an abrupt change in the volume of the system. So, we can say that during the phase transition, the two minima phi 1 and phi 2 vary with temperature at different rates, so that the entropy of one well is partial phi 1 over partial T, and well 2 is partial phi 2 partial T, and both of these entropies will be different because phi 1 and phi 2 represents the energies of two different phases, so they will be different. So when the system goes from one phase to another, the entropy changes, which gives rise to a latent heat, which is defined as T delta S, and this T is the transition temperature, which is noted by TP in this case. So this is basically the second law of thermodynamics, which is defined as dq is equal to T delta S. So that dq is basically the latent heat in this case. So whenever there is a discontinuity at the phase transition in thermodynamic potential, or whenever there is a latent heat involved, we say that there will be a first order phase transition. So this phase transition can also be represented in terms of a phase diagram. So here let's draw a curve between pressure and temperature, and we know that uh, when we are in this region, that is the region where we have high pressures and low temperatures, the system will exist in the solid form. Whereas on the other extreme and at higher temperatures and low pressures, the system will exist in the gaseous form. Whereas in between, the system will be present in the liquid form. So, one thing to note about these phase transitions or different phases is that the stable phase in this region is the solid phase, whereas the stable phase in this region is the liquid phase. So this basically is the phase transition temperature or the phase transition line, that if we increase further temperature, this solid will go into a liquid, and after this certain temperature, this liquid will go into the gaseous state. That is, for example, if I take a block of ice and I increase the temperature of the ice, that the temperature will rise, and at this point the ice will start to melt, and this temperature will correspond to 0 degrees Celsius, and on further increasing the temperature, this basically the solid, when it will convert into a liquid after the phase transition, when it absorbs latent heat, and then the temperature of the system will further increase, and it will increase a certain region where this region where the water will turns to a gas. So this is the basically this will correspond to the 100 degrees Celsius temperature. So this curve uh, can be slightly different for different kinds of compound, but on a whole, it will have a similar shape as we have shown in this figure. So the other important point is that that this line, that is the line between the solid and the liquid phase, it goes forever, whereas the line which exists between the liquid and the gas phases, it terminates at a certain point, which is known as the critical point. That if we increase the further temperature after the critical point, it means that there will be no distinction between the gas and the liquid, and you can say that the system will exist in a super fluid state. You cannot distinguish that whether it is a gas, it is in gas state or the liquid state. How you can distinguish between different phases, for example a solid or liquid, we can clearly distinguish the boundary of a solid and liquid, because there will be a boundary between the solid and liquid, so we can distinguish between these phases. And similarly we can also distinguish between liquid and gas, because there will be a boundary between these phases as well. For example, a meniscus will be there on the surface of water, by which we can distinguish that this is this is the upper layer of the liquid, and this is the region where the gas starts. But when you are in this region, you cannot distinguish between a liquid and a gas. So this is very important, and this is very interesting thing, and this can be experimentally seen. It's not difficult to verify this experimentally. So this region, um, this region up to a certain temperature Tc, um, um, there is a discontinuity at the phase transition. So this region is basically related to the first order phase transition. That is, all the properties of the system changes when you move from this liquid state to the gaseous state, because there is an abrupt change in, for example, the density of the liquid when you go from liquid state to the gaseous state. So such discontinuity is associated with the first order phase transition. Whereas after this critical point, whenever where there is no distinction between these two phases, so it means that we can regard this as a continuous phase transition, which is known as a second order phase transition. So on these lines, both of these phases can coexist. That is, the liquid and solid phase, liquid and gas phase can coexist on this line, whereas on this line, liquid and solid can coexist. Whereas on this line, solid and gas can coexist. And this coexistence can give you a different information about the system. For example, if we are at this point, the Gibbs free energy of the system of one phase will be equal to the Gibbs free energy of the other system as well, because both these systems are stable on this line. And this can give us different information about that thermodynamic system. Another important point to note is that is this point, which is known as the triple point, that at this point all three phases can coexist, and this point is known as the triple point, and the temperature corresponding to this point is noted as T3, and the pressure is noted as P3, whereas the pressure corresponding to the critical point is known as is noted by PC, and the temperature is noted by PC. So as I mentioned here, that this this liquid and gas coexistence at this liquid gas curve can give you different information about the thermodynamic system, and similarly this can also give you different information about thermodynamic system. So let's uh, discuss about the Clapeyron equation, and we will drive an expression of which was derived by Clapeyron, which is again based on the information that at this line both phases can coexist. So we know that when a system is on a phase boundary line, the two phases can coexist in equilibrium. If two phases are in equilibrium, we know that there will be their chemical potentials mu1 and mu2 are will be equal, and that gives free energy, which is given by G is equals to mu n will also be the same. So suppose that at one point of the phase boundary line, one point of the phase boundary line occurs at temperature T and pressure P, and another occurs at temperature T plus dt and pressure P plus dP. That is, let's consider this point and this point. So at this point, let's note the temperature as T and pressure as P, and at this point the temperature will be T plus Dt and pressure will be P plus dP. And we know that since both these points lie on this curve, it means that the Gibbs free energies at both these points will be same. So we can write that G1 is G1 Tp will be equal to G2 Tp, and G1 T plus P plus dP will be equal to G2 T plus dt P plus dP. And we can use Taylor expansion if dt is small. So by Taylor expansion, we will get partial G1 by partial T at constant pressure dt, and partial G1 by partial P uh, at constant temperature into dP. And similarly on the right hand side, and if we rearrange this above equation, we will get this equation. And we also know that um, a small change in the Gibbs free energy is equals to minus S dt plus V dP. So in this case, V will be equal to partial G by partial P at constant T, and S will be equal to minus partial G by partial T. So rearranging the last equation, we will get this expression, and putting the values of partial g1 by partial t and partial g2 by partial t at constant p, we will get s1 minus s2 divided by v1 minus v2, where s1 minus s2 is the change in entropies of the system, whereas v1 and v2 are the changes in the volume. That is, they are difference in they represent the difference in molar volumes at the phase transition. So we can write above expression as dP by dt is equals to L12 divided by dP into delta V, where delta V is equals to V1 minus V2, and S1 minus S2 will be equal to L12 divided by dP. So this equation is known as the Clapeyron equation, which can be verified experimentally as well. So this equation shows that uh, the slope dP by dt will be zero as L12, and that is the latent heat is equal to zero. And also we can see is that if the latent heat uh, no, that point we have already discussed. So that's all for this lecture. And in next lecture, I will discuss a few questions about the phase transitions, and then we will move towards the second order phase transitions. So that's all for this lecture. Thank you.